Hello, dear cadets. We Good morning to everyone. We already have seen the two cases of cantilever for slope and deflection. One is for point load and another is for uniformly distributed load. Now we'll see the last case of cantilever of uniformly varying load, for which we'll find the maximum slope and deflection by double integration method. So this is the last case of the double integration method. All the three cases of simply supported beam are already over. This is the last of the cantilever. Okay. Case number 3 as written here, that cantilever of the length L carrying a load whose intensity varies uniformly from 0. So 0 at the free end. So it is taken 0 at the free end B to W per unit run. W per unit run is the load intensity at the fixed end. So it is shown here at the fixed end and it is uniformly varying. That's why straight line is drawn from A to B. So right angle triangle will be formed. Right, so it is the diagram which is showing load as per the given case. So we have drawn here first the cantilever AB, you can see, of the length L, and the load value of the intensity is 0 at the free end B and uniformly varies by straight line to W per unit run at the fixed end A. Okay, first step is always to take a section and the load on one of the parts, either right or left. So in case of the triangles, we always take a section capital X at the distance small x from the pre-end. Why from the pre-end? Because if you see on the right part, the small triangle is formed. If you see on the left part, trapezium is formed. So the calculations are easy for the triangle than the trapezium. So always a triangle part we need to consider. That's why always the section is being taken on the pre-end side. If on the left end if we take, we have to go in the larger, or you can say the critical calculation than the righter part. Okay, so first step is taking section as shown in figure here. After taking section, what we need to find is the load which is acting on this right part of the section. To find the load on the right part of the section, we shall know the height. Height means the section value or this value at the distance x. So that is unknown now. So we have considered the load intensity at the height as Wx. Why we need to find this height? Because the load on the triangle is nothing but the area of the triangle. And area is 1/2 base into height. So we need to find this unknown Wx. How can we find this unknown Wx? So we can observe here, this is the smaller triangle and this is the larger one. Both these triangles are similar triangle. Okay, if we apply the similar triangle principle, we can simply find Wx. So let us apply similar triangle here. That will be Wx by x is equal to W by L. So same is written here. Wx by x is equal to W by L. So load intensity Wx will be W into x by L. This is the value of the height. Okay. Once we get the height, base is already known. So area we can find. So load on Bx, span Bx will simply become the area, that is area of the small triangle, 1/2 x into Wx. If you replace this Wx by W into x by L, we'll get the load on the righter part as this. What is it? It is coming Wx square by 2L at the centroid. Centroid is always at the x by 3 from the section. Okay, so here on the right part now we have got the load that is coming as Wx square by 2L at x by 3 from the section. So once we get this load, our next step is to show this load on the right part. Okay, it has got from similar triangle principle. You can note it down. So I suggest all of you to keep the pen and notebook with you when you watch the video so that you can simultaneously write it. So I will now move to the next step after finding the total load on the right part of the section on the span Bx. Now to simplify this, I have again drawn the diagram. Okay, again the same cantilever is shown. On the righter part, I have shown the calculated load wx square by 2l here at the x by 3, that is at centroid from the section. This load is important. Why? Because to find the bending moment equation, we need the load on the right part. So that is calculated. Okay, once we know the load on Bx, now we can write the bending moment equation on this right part. It is always force into distance. So bending moment equation is always starting from this EI d square y by dx square is equal to total bending moment at the section x. So see what is it? It is nothing but wx square by 2l into x by 3. Same is written here, wx square by 2l into x by 3. That becomes wx cube by 6l. Minus sign shows the downward moment. Okay. Now integrate this to get the slope equation. Integrate this one integrate it. So by general integration rule, w by 6l will be constant. Integration of x cube is x raised to 4 by 4 plus c1 is the first constant of integration. Let it be equation number 1. Okay. Now after writing this equation, we can find the unknown c1, which is constant. To find c1, we always use the known condition. What is known condition we have? You can see here at the fixed end. At the fixed end, there is no deflection. So at the fixed end, x is L. So we can write at the x is L, there is no deflection as well as there is no slope also. So the slope equation will be at x is equal to L, dy by dx is equal to 0. That is at the fixed end A. So same is written here. To find C1, put x is equal to L and dy by dx equal to 0 at the fixed end. Okay. So if you put these values here, this in the equation number 1, put x is equal to 0, so this will be cancelled, only c1 will remain. X is equal to L, then the value of c1 what we will get is this, minus will be becoming plus on the other side. So c1 is WL cube by 24. You can check it mathematically. Once we get c1, put the constant c1 back in this equation number 1. So let us put it c1 in the equation number 1. So here if you put, numerator is wx raised to 4 by, and denominator is 24 by 24l. Minus sign is there, which is missed here. It is written. Okay. And c1 is same, wl cube by 24. So this is the general expression for the slope we have got. You can check this mathematically. It is the general expression means what? It is applicable to any point between a and b, that is from 0 to L. We can find the slopes. Now slope at A is already known because at the fixed end it is 0. So what we have to find is slope at the other end, that is at B. So to find the slope at the free A and B, x is 0, we know it from the diagram. So put it x is equal to 0. So first term will be naturally cancelled. What remains is the second term only, that is WL cube by 24. So this is the slope value at the free A and B, which is nothing but the maximum slope will be getting at the B. This value is coming positive. What does it mean by positive sign? It means if you draw a tangent to the curve, okay, at the point B, it will be making the angle with the beam in the positive direction. Okay, so that is the value of slope at the A and B, which is maximum slope. Now slope part is over. Our next part is to find the slope, equation for deflection. To find the equation for deflection, integrate the slope equation. This is the slope equation, equation number 2, integrate it. So w by 24 L is constant, integration of x raised to 4 will be x raised to 5 by 5, WL cube by 24 into x plus C2 will be introduced, is it? By general integration rule, we get the equation number 3. Check it mathematically. Okay, once we get this equation, we again have to find the constant C2, which is unknown. To find constant C2, we always use the known condition. What is the known condition? Which is already noted. Put x is equal to L, y equal to 0. At the fixed end A, we know x is L, and at the fixed end there is no deflection, so y is 0. Put it here. So x is 0, x is 0. So both these terms are cancelled. What remains is third term only. Putting x is equal to L, you have to mathematically simplify it by taking LCM, etc. So C2 will have some value, it will not become 0. So C2 will be coming this. Is it coming? You can check it mathematically. After getting C2, put back this C2 in the expression of EIY. So I have taken C2 here. You can check it. This will be our general expression for EIY, which is applicable to any point between A and B, that is from 0 to L. So this is our last expression, expression number 4, from which we can find the Y max. Okay. So where the Y max will come? In all the cases of cantilever, Y max is always coming at the free end. So free end is B. So to get Y is equal to Y max, at B, that is at the free end B, X is always 0. Put it in the expression number 4. Now these two terms will be coming 0 and only remains is the last term minus WL raised to 4 by 30. So Y max at the free end B will come this. Again downward direction is there. That's why minus sign is coming. So this is the expression for maximum deflection. So all the cases of simply supported beam and cantilever are now over by double integration method. Refer the problems which are given in the notes, which is already uploaded on ERP and also on the WhatsApp groups. So kindly refer those notes. Uh, Only Macaulay's method for finding slope and deflection, in that only 2 to 3 cases we have to do, that will be doing in the next lectures. So refer these notes and work on it. Okay. So 90% of the syllabus of slope and deflection of the beam is over. Only 10% remains. That is Macaulay's method, and 2 to 3 problems on the same we can take it on it. We can take on it. Okay. Thank you.